So let's talk about linear regression analysis. If you recall from your prior instruction, probably in Stats 1, if you took it with me or if you took it, whether it's undergrad or grad, we talked about linear regression analysis. If you took it from somebody else, I'm sure they talked about it as well. Linear regression can be divided into two types. There's one is simple and the other is multiple, but one is just an extension of the other. Simple regression analysis, we have one predictor variable and one outcome variable. Let's look at the way the symbols here and just make sure you understand what they mean. First of all, we have an outcome and a predictor. So this is an equation for a line. You should be familiar with the equation for a line. You may have learned about it in high school, middle school, elementary school. I have no idea. Generally, it's something like y equals mx plus b, right? So there's a slope and an intercept and an outcome. So this is the outcome variable. Generally, we use y. It's random. You could use any letter you want, but there's always some consistency of what people tend to use. So the y represents the outcome, and x represents a predictor in this case. Now, because we're going to use x multiple times, we'll label each variable with a number. So the x1 would be the first variable entered in the model, etc., etc. That's rather than using xy, xh, lm, or whatever we want to use. We'll just try to use this subscripted number in order to denote which variable we have. The hat on the y indicates that it's a predicted value rather than an observed value. So like here it's y sub I, there's no hat on that. This means an observed value. So we look in the data, we see the value, that's an observed value. The I subscript means individual something, individual unit, whether it's person, cat, school, whatever, car, whatever we're studying. So it's an individual value. So we have y hat, so this is an estimated outcome, and this outcome is predicted by some variable called x1 sub I. So the I indicates that both the individual, the predictor variable and the outcome are individualized. So each individual has her own value on these two variables. You'll notice that we have these two b values. The first b sub 0 is our intercept value. This is where the line crosses the y-axis. You'll also notice that the two b's do not have i's by them. So what this means is that they're not individualized. They are assumed to be the same for everybody, which is problematic in statistics, but we'll talk about that later. The b sub 1 is your slope value. You probably remember slope is rise over run or gradient, whatever you want to call it. So this indicates how the predictor is related to the outcome. So if a predictor is 0, then the best estimate of y would be just the intercept value. So let's keep that in mind. There is a relation between the b, so these are parameter estimates, right? Just like any statistic, they're estimating some population parameters. We'll call these parameter estimates. There's a relation between the parameter estimate for our slope and simple regression. Simple regression, if you recall, is where we correlate. Simple correlation. Correlation is where we correlate two variables together, right? So we see how they move in relation to one another, how each variable moves in relation to the other, right? So if, for instance, we're correlating ice cream consumption with weight, they'll be positively correlated. The more ice cream you eat, the more you weigh. If we correlate hours of exercise with weight, probably they're negatively related. The more exercise you do, the less you weigh. The equation, and again, we're not really doing math in this course, but you should be familiar with the way we derive these values. So the correlation is a standardized covariance. A covariance is an unstandardized correlation, so it's in the original units of measurement. So for instance, if we're doing hours of exercise and weight, hours of exercise is in hours, that's its unit, and weight could be in pounds, right? So covariances are very difficult to relate to one another because of the units. When we divide by the standard deviation of each, we remove the units and we have a unit-less measure, and that's what our correlation is. So correlation is a standardized covariance. If we use the correlation, we can, and the standard deviations, we can derive our estimate of the slope, our parameter estimate for the slope. The intercept value, though, is, in order to get that, we just rearrange the equation here, and we can actually solve for it. It's pretty easy to do, right? So we want to solve for B0, so we subtract this value from each side, and we isolate the B0. Shifting it to the left makes us be able to read it from left to right. To estimate y and x, what we do is we use the mean value. The mean is always the best estimate in the absence of any other information of a variable. So then we can solve for B0. Once we have that, we can write this equation. You may wonder, why do we want to write out the equation? Well, it has value for individuals who are trying to make predictions. We can actually get somebody's predicted value on something once we have the equation. In terms of multiple regression, we add more predictors. So in this case, we're estimating our outcome. Here's the y hat sub I from k theoretically plausible predictor variables. And notice how I say theoretically plausible. That'll come into play later. So I can have, in theory, I could have up to an infinite number of predictor variables, but that's not a good idea. So in this case, you'll notice how the x's are subscripted with these values going all the way up to k. So we use k to indicate the largest possible value. When we move from the prediction equation to the predicted value, you'll notice that the hat disappears, right? But we have this addition of an E sub I. The E sub I is an error term, also known as residual. So this is the term that we'll be using a lot in our diagnostic of regression, but this is the leftover. So this is the part of the model that's not accounted for by the predictors. And obviously we'd like to make this as small as possible, the errors. All right, so let's see. I talked about all this. Just in case you can't remember or you don't know what a slope and an intercept are, these are examples of three lines with different intercepts because they cross the y-axis at different points but the same slope. You see the gradient is the same. This is an example of two lines with the same intercept. They cross the y-axis at the same point, but they have different slopes. One is positive and one is negative. The E sub I, as I mentioned before, those are residual terms, so those are leftover terms. So if you want to calculate E sub I, you go y sub I minus the y sub I with the hat. I probably should have put that up here. For some reason, I thought it would fit better over there. But yeah, I guess because I was talking about what the points were. So it's the difference between these two equations. Makes sense, right? One subtracting the other, we'll just have the E sub I left over. Now let's talk about regression assumptions. So here's some basic assumptions that have to be met. The outcome variable must be continuous. If we're using a categorical variable or any kind of discrete variable, we'll have a different type of regression, and we'll talk about logistic regression later when we're dealing with discrete categorical variables. Predictors, though, it doesn't matter what they are. They can be discrete or continuous as long as you know what the scaling is so you can interpret them correctly. We assume that the predictors have non-zero variance, which makes sense. If they had zero variance, they wouldn't be variables, they would be constants, so that wouldn't really do anything for us. We assume there's a linear relation between the predictor and the outcome, although we can deal with nonlinear. And we can do nonlinear regression, and it's done quite frequently, actually. You might add quadratic terms. We'll get to that at some point later in the course. We assume that all values of the outcome should come from different people, so there's independence, right? Homoscedasticity, so for each value of the predictors, the variance of the error should be constant. So we don't want to have different degree of variability at different levels of the predictor variable. So in other words, if there's differences in variability across different levels of the predictor, then say at one extreme of the predictor, you may do a better job of predicting the outcome than in another. So if we're predicting hours of the effect of exercise on one's weight, imagine that you do a better job at predicting one's weight at lower levels of exercise, hours per week, than you do at higher hours of exercise per week. That wouldn't really do. We want to be consistent across different levels of our predictor. And our errors are assumed, so the E sub I, they're assumed to be normally distributed with a mean of 0. We also would like there to be no multicollinearity in the predictors. We'll talk about multicollinearity. That means that the predictors are correlated or highly correlated. We actually would not like that because then they'd be measuring the same thing. So we want them to measure each predictor to measure something different. So again, we'll cover this more shortly. In terms of how do we interpret regression coefficients, well, for the unstandardized regression coefficients, we need to understand the units of measurement. So here's an example. So suppose we have a following equation with confidence predicting race time. So race time is in seconds, and lower times are better when you're racing, and confidence is ranging 0 to 10, right? With 0 being the lowest. So the way we would interpret this is that, and it's very important that you do this correctly. Each unit increase, I didn't say decrease, each unit increase in confidence, so from 0 to 10, is associated with a 0.02 decrease in race time. 0.02 second decrease in race time, because the race time is in seconds. Now, if there were more variables here, we'd say holding all other variables constant, but this is a simple regression model with only one predictor. We can also use standardized predictor variables, and we'll talk about that more next class when I show you some examples. If we use standardized values, in this case, this our standardized version of this b value, and we use beta to represent standardized values. And again, I'll use parameter estimate or something like that for the b's, because I want to make sure that there's you separate them from the standardized versions. Let's say the standardized version is negative 0.5. So we'd have the same equation, but you'd have a negative 0.5 here instead of minus 0.2. I would read this as follows. Each standard deviation increase in confidence results in a 0.5 is half standard deviation decrease in race time. I should add, though, that, well, a couple things. First of all, the standardized effects have an advantage over the unstandardized, because the standardized effects, they can be compared, so you can see the effect of one variable versus the other, because I don't have to worry about the units of measurement, so I can make direct comparisons. I can look at all my variables and see which one has a stronger effect by looking at the standardized effects. So that's something that's extremely important when it comes to using standardized variables. And let's see, there was something else I wanted to say, but it just slipped my mind right now. I'll get back to it later. Let's see. All right. So those are interpretations. So you want to make sure you understand how to interpret these effects. Okay, let's look at some regression diagnostics. So we want to make sure that everything is okay. We're meeting the assumptions. Right. So that's why we diagnose, and also we have to look out for errors that are made in data entry, and those can be seen when we're doing these diagnostics. So first of all, let's look at multicollinearity. So again, that's when the variables are highly correlated. Problem with multicollinearity is that it'll inflate our standard errors. All these equations in statistics are generally model divided by error. So that you'll see that most of them are a quotient, right? You have a numerator and a denominator. And the denominator is generally an error term, because we want the model to do a better job predicting than it doesn't. So that's how we do our calculation. And denominator is generally standard error. See last lecture where I talked about what a standard error is. So if we inflate, that means it get larger, our standard errors, it'll be more difficult to reject the null hypothesis, right? So that we will be committing a type 2 error. We can look at correlations to diagnose multicollinearity, although that can be kind of difficult because correlation matrices are really, they have a lot of numbers in them, and sometimes your eyes can go crazy when you look at a correlation matrix. But if we do look at a correlation matrix, we're looking for high values like 0.8 and above. And if you read hopefully you did, read the handout I provided the other day. On that handout, it was a a link I provided, there's a good discussion of this and a demonstration of what a high correlation looks like in multicollinearity. Other estimates of multicollinearity are tolerance and the variance inflation factor. Tolerance is the proportion of the variance of a predictor not accounted for by the other predicted variables. So in essence, what you're doing is a regression analysis among the predictors, excluding the outcome variable, and you're trying to see if they're highly correlated. So you're calculating what's known as an R-squared, right? A proportion of the variance accounted for by the other predictors, and we'd like that to be the proportion unaccounted for to be high, right? We want that to be high. So larger values of tolerance are better, and then the reciprocal of tolerance is the variance inflation factor. So obviously we want this to be small instead of large, right? And here's some heuristics for it. So tolerance values less than 0.1 are troubling, and for VIF values greater than 10 are worrying. So what do we do if we suspect multicollinearity? Now we should go look at the correlations to see what they're like, and we could remove the variable that may be troubling and then re-examine the standard error. So we want to see what happens to the standard errors. And again, there was a good example in the IDRE link that I sent you the other day, the UCLA link that I sent you the other day. I just want to check for homoscedasticity. So this is what I just talked about earlier, where we want the variability around the outcome to be consistent at different levels of the predictor variable. And we can do a plot. We can plot Z residual. So Z means standardized, right? Because Z value is a standardized value. The residuals, so we can't look at Y directly because Y doesn't really exist anymore. Now it's a predicted value. So Y has been changed by the model, so the only thing that's left over is the residuals. We look at the residuals versus the standardized predictor value. All right, let's talk. I'll get back to building the regression equation in a little bit. I'll talk about this more in a little bit. Just hang on a bit here. So let's do an example. This is an example from another textbook that I used to use. It's on record sales. So a record company boss was interested in predicting album sales from advertising. So the data are 200 different album releases. The outcome variable is sales, like CDs or downloads in a week after release. And the predictor variables are the amount of, and this is a British textbook, so the amount of pounds spent promoting the album before release, at this advertising budget, the number of plays on the radio, and the image of the band. In simple regression, we're only looking at one predictor, so in this case, we'll start with this advertising budget as the single predictor variable. So if we look at this figure here, I'm going to shrink the screen size a little bit so it fits on one slide. So if we look at this image here, we can see that, and this is just a simple scatter plot. A scatter plot just plots the two variables so that each of these dots represents the intersection of 2 points. Like this is $500 spent, $500,000 or pounds spent on advertising, and somewhere around 25, 30 records sold, right? So this is the intersection between the two. And if we plot the best fitting line, this is the line that minimizes the difference between each point and the line. You see we have a linear relation here. I mean, you could try, and again, in the example the link that I sent you, there's a way to show you how you do what's called a LOESS curve, and you can actually try to fit a more precise line that's not necessarily linear, but again, it's not necessary at this point because this looks like a straight line will fit it pretty well. And here, this is the R squared. In case you can't remember, R squared in correlation is the proportion of shared variance between two variables. We use it in regression analysis as well, so it's the proportion of the variance in the outcome variable that's accounted for by the predictor variable. So it's basically the same measure. If we had more than one variable, it would be more difficult to visualize the relation because now we have to look at a plane rather than a straight line. So eventually we run out of dimensions and we can't visualize them anymore. So so the next step would be to estimate the fit of the model to the data. We always say fit of the model to the data. How well does the model fit? Because we have, basically this is a model that we're saying predicts the relation. So we want to look at the fit of the model to the data, and we use the familiar F statistic. The F statistic is, if you recall from analysis of variance, sure you've seen this before if you took any stats course. It's the mean square model divided by the mean square residual. And just as I mentioned a moment ago, all test statistics are model divided by error. So residual is synonymous for error. And this is the R square I just mentioned. The way it's calculated here is the sum of squares of the model divided by the sum of squares total. So how much of the variability? So again, the model, the total is actually, if you look down here, is the model plus the residual sum of squares. So this is just basically this component, the model divided by the total. So it tells me what proportion of the variation in the model, in the outcome, is accounted for by the model. So this is a breakdown of the terms in an ANOVA table. When we run the model next class, you'll see the ANOVA table for regression, and we'll be able to discuss each of those terms. And just for now, though, just for you to understand how we derive this equation, and you should always know how to derive everything, even if you're not calculating it by hand. The mean square residual is the sum of square residuals divided by its degrees of freedom, where the degrees of freedom are n minus k minus 1, and k is the number of variables in the predictor variables in the model. So this is a lot like what you saw in ANOVA, where k was the number of groups in this case. In the case of ANOVA, and then so that's the residual mean square model is just sum of square model divided. So it's always the model, in this case, to calculate these means, because you're actually basically you're dividing by n, right? But you're not going to have an infinite number of predictors. So in this case, the model, the mean square model, is model divided by the degrees of freedom. And let's see, so these are the equations for the total. And this is actually a nice picture of what each of these sums of squares. You'll notice that in these equations, the sum of square is in the numerator and degrees of freedom is in the denominator. So in this case, the sum of squares is, this is the total sum of squares. Again, in this equation, you have sum of squares total equals sum of squares model plus sum of squares residual. So this is the total sum of squares. Total sum of squares is the difference between each point and the overall mean. Then we have the sum of square residuals. So the residuals indicate how well we predicted it. Again, we saw an example of residual being the error term, right? So it's the difference between each value and the predicted value. And finally, the model sum of squares is the difference between the mean and each predicted value. To assess the significance of in regression analysis, although we can look at the model through the ANOVA table, and I just mentioned that a moment ago, what we will do instead is we're more interested actually in the predictor. That's why we do regression. We want to know if the predictors are significant. The null and alternative hypotheses for our to estimate to assess the significance of our predictor variable. The null is b is equal to 0, and the alternative is b is not equal to 0. So just to break this down for you, the reason we do b is equal to 0 because we have to assume that there is no effect. We always start with the assumption that there is no effect, so we assume that the parameter estimate associated with any variable is 0. So it absolutely has no effect. The alternative is that it does have an effect, and this is a two-sided alternative in this case. Our test statistic is the t statistic because we don't have the population standard deviation, but we do have the population estimate. In this case, b is equal to 0, right? So the equation is b observed minus b expected, and if we're expecting it to be 0, right? So it's just going to be b observed divided by the standard error of b. So it's your regular one sample t statistic. Okay, so let's talk a little bit more about outliers and other problematic effects. So what's an outlier? An outlier is a case that has a very high residual, right? Has very high residual. So what represents a high residual could be anywhere from 2 to 3 standard deviations from the mean. So the error, it has a very high error term. So the predicted value is very different from the actual value. And here's an example where we have the regression line in blue, and then we have this residual, right? Very high residual, and this is somebody's outcome. And notice how it's very far away from the rest of the outcomes. It's so far away that it shifts the best fit line downwards, so it has an impact on our prediction, right? So we look for these outliers, we estimate, we look at our standardized residuals, standardized, because we know in standardized terms that we know that empirical rule that 68% of all values are between plus or minus 1 standard deviation of the mean, 95% are between plus or minus 2 standard deviations of the mean, and 99.7% of all values are within plus or minus 3 standard deviations of the mean. So we can test this using the standardized residuals to see how far away it is from the mean, and then we use some kind of heuristic, whether it's 2 or 3 standard deviations. It just tells us that we should look at the value. It doesn't mean we should eliminate them. We also look for influential cases and leverage. Leverage is the difference between, so this is now we're dealing with the predictor rather than the predicted value. We're looking for values that are very different on a predictor from the mean of that predictor. So high leverage means that there's a larger difference between the mean of a predictor variable and its actual value. Leverage values, you'd want to investigate them if they are above this heuristic 2k plus 1 divided by n, where k is the number of predictors. So there's all these heuristics that have been found to indicate what we should look after. Again, doesn't mean we're going to remove that case. We just want to look at it, investigate it. We can also use this analysis of influential cases. There's 2 ways we can do it. A more general way is something called a Cook's distance. Measures how much influence a case has on the model in total, both the estimate and the predictor, the parameter coefficients, right? The B's, right? Both of them, that's Cook's distance. The traditional cutoff is 4 divided by n, where n is the sample size. Another one is any one above 1, so you can use whatever you prefer in that case. Again, that means you're going to investigate that value. By the way, if you have these values being large, it could be that you just have a data entry error, right? Instead of 20 minutes, you put 200 minutes or something like that. You can also look at the difference in betas. DF beta stands for difference in betas. DF stands for difference. So this just looks at what will happen with or without the case in the model, right? So it removes it and it puts it back in and see what the difference is in the beta. And this looks at a specific variable, and you'll notice that another cutoff here is 2 divided by square root of n. All right, so the only thing we should do if we find any cases that are troubling is we take a look at them. That's it. We just want to see if if they are problematic. We don't just remove cases from an analysis because cases are very difficult to acquire. We put a lot of work and effort into acquiring these cases, so we have to do an overall assessment. If we find that they're extremely problematic, we can remove them. That's it, but again, we should do that very cautiously. All right, that is all. Thank you.